Cool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome to this session on synergy between geography and mapping with the nation's energy mission. My name is Andrea Manara from the ITU, the International Telecommunication Union, and it is an honor for me to introduce a new episode in the GeoAI Discovery series. This series is curated by three outstanding geospatial professionals, Nadina Lamé, Maria Brovelli, and Barbara Ryan. We launched this series on February the 1st, and we discussed the GeoAI applications and policies, ethics, and the future of GeoAI for Good. Thematic sessions included climate actions and GeoAI, spatial digital twins and GeoAI, GeoAI and the digital transformation of agriculture, water, and food systems, and machine learning supporting ecology. If you missed some episodes, don't worry. You can watch the recordings of those events on YouTube or on the neural network to which you are connected right now. Without further ado, let me now introduce Maria Brovelli. She is a professor of GIS at the Politecnico di Milano and a member of School of Doctoral Studies in Data Science at Roma La Sapienza. Amongst her many activities, Maria is also a member of the Advisory Committee of Earth Observation, chair of the UN Global Geospatial Information Management Academic Network, and co-chair of the United Nations Open GIS initiatives. She will moderate these sessions and introduce you to the outstanding speaker of today's session. Maria, the floor is yours.
Thank you, Andrea, and welcome to everyone. Good day, good afternoon, good morning to everyone. And I'm very happy to have you here again. And also, I'm very pleased and honored of having here our guest. You see him here. So hello, Budu. Thank you for being here with us. And before starting, I want to give a very short presentation of you for the very few people who don't know you, because as a matter of fact, Budu is very famous and very important in the geospatial field. Anyway, for the few people who have not known Budu Baduri, He is a corporate research fellow and the director of the Geospatial Science and Human Security Division at Oak Ridge National Laboratory. In that capacity, he is responsible for a research portfolio focusing on novel implementation of geospatial science and technology across energy, environment, and national security missions across the US government agencies. Dr. Badouri is a fellow of the American Association for Advancement of Science, the American Association of Geographers, and currently serves on the Geographical Science Committee of the National Academy of Science. He's a founding member of the US Department of Energy's Geospatial Science Steering Committee and is a recipient of the department's Outstanding Mentor Award for his dedicated service to the department for developing future workforce for the nation. Dr. Badouri received his PhD in Earth and Atmospheric Science from the Purdue University. He has a Master of Science from the Kent State University, a Master of Science, and a Bachelor in Geology from University of Calcutta, India. So, Budu, very welcome to this session, to this panel. I'm really excited and looking forward to your speech. And your speech will be about geography and mapping with the nation's energy mission. So thank you so much for being here with us, Budu.
Thank you, Maria. The honor is all mine. I am delighted to be here and speaking to all of you, as well as a global audience. Let me quickly share my screen. So I chose this topic for a variety of reasons because as we all recognize that AI, in particular GeoAI, has become a very pervasive technology. Just as an anecdote, I can take a little credit for the fact that the term GeoAI, I have seen the birth of that term in my office. I had a distinguished science fellow called Huina Mao. She wrote a proposal to SEM6 Spatial in 2016 for doing AI in geospatial applications. Her proposal was accepted, except the organizers wanted a more catchy term. So Huina and I were discussing this, and she came up with the term GeoAI. And since then, it has become a global word for the community. So I'm particularly honored and delighted to be part of this community from the early on. So what I wanted to do is first—
Sorry, Budu, just to quickly jump in. Could you go to the beginning of your presentation?
I am sharing my presentation, right?
You are, but we're on the
Not yet,
slide.
not yet.
We just need to go into presentation mode and then go to
This is the last slide.
There we go.
Okay.
Is it good?
Yep.
Yeah,
Okay.
thank you.
All right, sorry about that. I just wanted to quickly introduce what Oak Ridge National Laboratory is and why we participate in a geographical and geospatial sciences here. So as many of you may know, that the US Department of Energy's National Lab Systems, we all came out of the Manhattan Project. That was a landmark event in human history during the Second World War. Oak Ridge was one of the 3 sites around the nation with the particular objective of creating enriched plutonium. And the Clinton pile at the time, what it was called, was the first continuously operated nuclear reactor in the world. So the whole objective was that, to develop these chemical processing techniques that would separate plutonium from irradiated fuel. And so we all know the rest of the history of how that unfolded for human civilization. But in 1948, the Clinton laboratory at the time, what was called, became Oak Ridge National Laboratory. This is one of those old pictures of workers working in the Clinton pile trying to enrich plutonium. So geography was actually part of this Manhattan Project from early days. Today we figure, site selection and siting in geospatial analysis as one of the fundamental applications. But if you look at in the early 1940s about how these three particular locations were chosen to execute the Manhattan Project, they were not just a random choice. They were all geographically informed site selection process that led to Oak Ridge, Los Alamos in New Mexico, and the Hanford site in Washington. So today, after 80 years of science and technology history, all the national labs, there were 17 of them, are part of this discovery of innovation in science and technology in the US and perhaps the world. So there are a number of these national labs that are dedicated to the science mission of the department. Oak Ridge is the largest multi-purpose science lab amongst all the Office of Science labs. We have a few labs that support the energy mission of the department. National Renewable Energy Lab in Denver, Idaho National Lab in Idaho Falls, Idaho, and the National Energy Technology Lab in Morgantown, West Virginia. There are 3 labs that support the nuclear and national security mission of the department: Lawrence Livermore in California and Los Alamos and Sandia in New Mexico. And then there is one national lab that is dedicated towards the environmental management mission of the department because of the waste management aspects of the nuclear business, which is in Savannah River National Lab. So 80 years later, this is how we look. We are set in a beautiful landscape of East Tennessee. It's about 40,000 acres of the reservation, surrounded by the Clinch River, and about $2.6 billion of annual budget, and about 6,000 people working to execute the science and technology mission. So the lab over the last 80 years have taken part in significant discoveries that has helped science, all the way from developing radioisotopes and stable isotopes that are still used in medical practice. So every time for cancer treatment, you use radiation treatment. The origin of the radiation treatment goes back to the early days of nuclear medicine at Oak Ridge. All the way to, today we are still discovering elements. One of the newest elements in the periodic table called tennessine that was discovered right here a few years back at Oak Ridge. But what I'm going to focus on today is our impact and history on developing applications in high-performance computing. So the organization that I lead, and I have worked here for about the last quarter century, 25 years, we have really fostered and tried to move the needle at the intersection of geospatial science, high-performance computing, and national missions in energy, environment, and national security. So if you think about how that area has progressed over the last 25 years, we have seen the advent and progress of really, really large computers. Oak Ridge is the largest supercomputing complex in the world. 3 floors down from where I'm sitting and talking, the #1 machine in the world called Frontier, and the number 5 or 6 machine that used to be the #1 machine called Summit. They are both residing on the first floor or the ground floor of the building that I am in. I'm straight sitting up from there. So where we have really made a significant impact and contributions to the community is advancing artificial intelligence, in particular geospatial artificial intelligence, or GeoAI. And there are many variety of applications areas, and my goal for the rest of the time is to walk you through some of these activities that are interesting in this mission. So I am only exposing a sliver of all the work that we do. but hopefully this is going to resonate in terms of this overall sustainable development goal. So many of you know us for the last quarter of a century for developing very high resolution population data for the world. Population estimations at a fine spatial and temporal resolution is foundational to meeting sustainable development goal, meeting human security, and elevating the quality of life for human civilizations across the planet. So we have been the frontiers in that respect of really making sure that everyone working around the world has access to the best possible data on population distribution and dynamics. So we have shared with the community a global data set called Landscan Global, which is at 30 arcsecond or 1 kilometer resolution. It is one of the few data sets that has had daily or yearly cadence every year, produced and shared with the community since year 2000, or 1999 was the first version. In early 2000s, we came up with a very high resolution version for the US, which was also the first ever attempt to separate nighttime or time variant population, both from a daytime distribution versus a nighttime distribution. We were all aware that this is a significant need for the community because, of the 24-hour period, we probably spend 1/3 or a little more at home, which is represented in the census data that has been the primary source of population data in the past. But the rest of the time when we are there, and this is an example of Washington, D.C., on a diurnal hourly basis, how the city lives and breathes. The reason I like this visual is to demonstrate that, while you might think of these as people populating a city and depopulating a city, this is also can be visualized as, a city's energy demand map, because as humans move around the landscape, we drive the energy demand for our mobility resources. How much, energy do we need to go from one place to the other? And as we are, dwelling at a place, we drive energy needs for buildings and, waters and everything else. So mid-2000s also saw us move towards a high resolution version for the whole world, which we call Landscan HD, high definition, which is at 90-meter resolution for the planet. We are in the process of creating it a global coverage. We have significant parts of the world already covered. And all the data set, I'm very proud to say, that is out there in the open at landscan.ornl.gov for the entire community to come and take part and use it. So it's completely publicly available to everyone. So when we first started doing this high resolution population data for the world, one of the simplest logic that we used is that if we could map all the buildings of the planet, then we have a very strong indication of where people are, because buildings don't grow in nature. If you see a building anywhere, that means humans have been out there. So that was the simple logic, and we started that journey in combining high performance computing and high resolution satellite imagery in the mid-2000s. So in one of the IGARs, we had the first ever paper that discussed high performance computing and extracting human settlements from satellite images. That was many years back in Barcelona. And it's interesting to think that that was the only paper that came from across the world. And today, if you go to any of the scientific meetings, it is wonderful to see how the whole community has embraced this technology that we thought that had a lot of potential for meeting the data needs for the community. So, but it's an incredibly challenging science proposition, because if you really want to know what a good example of a needle in a haystack problem is, it's probably finding buildings in a landscape, okay? And I'm throwing out a very simple statistics of two countries, Mali and Venezuela, which, for Mali, only 0.02% of the land is occupied by buildings, and in Venezuela, it's 0.13%. So finding buildings in a very large landscape at a country scale is a non-trivial exercise. But this is where we have made significant progress in two different ways. One, we have matured our algorithms significantly better, especially after the advent and popularity of the convolutional neural networks. And the second thing is that we have been able to couple that with the progress in high performance computing technology. So I'm giving you an example here to give you some sort of an idea about how good and how fast this mapping buildings have become. We took 12 nodes or 96 GPUs in the largest machine at that time, which was Summit, and we trained a model with 110,000 worldview labeled images and mapped every building in less than 45 minutes. So, and if you look at the newest version, which is on Volta GPUs, V100s, you can process in about 3 minutes, 35,000 by 35,000 pixels of a 4-band image. So in a more realistic term, you could use all buildings using the 3200 GPUs on Summit. And we have another benchmark where we mapped using Titan, which was the high performance computer before Summit, every building in Yemen in 1 hour and 41 minutes. So this is really, really promising in terms of generating vast data resources. So this process was also foundational for developing a developed country like the US. We processed about 60,000 images, about 74 trillion pixels for the entire 50 states to map for the first time the 125 million buildings that are 450 square feet or larger in the United States. Now, this is a significant feat for the nation, is because these buildings are, they become the foundations for understanding energy distribution, energy demand, energy production, energy delivery, and also disaster response. The 450 square feet, that minimum threshold was picked because that's the size of an average mobile home park or trailer home park, which are low income housing in the US, which often gets the first housing that gets impacted by flooding or storms or tornadoes. So that's what drove this. And these kinds of data sets really make, and this data set, by the way, is also openly accessible through the FEMA's Geo platform. These data sets support real decisions at the highest level of government. So here, right after the Mayfield, Kentucky tornado in December of 2021, you can see the FEMA administrator is briefing the president of the United States using a map that has the buildings that outlines that we produced out of using GeoAI on high resolution satellite images. So this is very, very impactful work for the nation. I wanted to also talk about a second order of applications of GeoAI that we are pursuing, which is once you have the buildings, what more can you talk about of any particular geography that is useful for sustainable development goals? This work, we call it delineating neighborhoods. So once you have the buildings, can you delineate different kinds of neighborhood patterns in a city based upon the scale of formality? So of course, the more formal the buildings are, that is stronger indications of wealth, socioeconomic strength, and also they are more energy demand, but there is also a lot more energy efficiency in those structures, as opposed to the very informal structures that you can find, which are low income, and then also a lot more energy inefficient. So these kinds of applications are producing very, very interesting data sets, and I'm going to only throw out one in this presentation. This is Rio de Janeiro, Brazil, and you can see, in a very, very fine details, the different kinds of neighborhoods that you can see in a particular city. And you can do this over time to understand, what kind of neighborhoods, what kind of socioeconomic strengths are increasing or decreasing in a particular place on Earth. So I talked about disaster response. As you can very easily understand that if you have a very good way of training your AI model to detect buildings, the AI model fails once the building changes. And so we are essentially applying that simple logic to understand very, very quickly how many buildings are being damaged after a disaster. And here is one example of a tornado track that essentially identified very quickly how many buildings were destroyed after the tornado passed through one area. And then the similar techniques also lead to assessment of, the general assessment of structures. Here is one example from Baga, Nigeria. And this particular algorithm looks at very low-level features that define individual structures in this landscape and does a very rapid count of how many possible structures might be in this particular scene. So here you can see, there are 10,790, and the automated count went to a post-event about 9,600. So if I zoom in, you will probably understand why this was so important. Baga, Nigeria, this region was impacted by the violence of Boko Haram. And so they burned down villages in a vast area. So if you look at this image, which the algorithm spit out 285 individual structures, after the burning, there were only 151 structures that was left. So these kinds of very rapid analysis provides a fantastic tools for the first responders or anyone who is trying to work in the disaster response and recovery domain. I wanted to also highlight the work that we have been doing in Ukraine, using very similar techniques of using AI to detect buildings and damaged buildings since the conflict started in February of 2021. We are delineating these buildings, looking at these building change maps. And here is a more closer look on how efficiently the algorithms are detecting changes on impacted building, destroyed buildings in a very large areas. And all this information is then going back out to refining the population estimates that we are making, that is going back into the Ukrainian government, through the US government, and also the different kinds of response and relief agencies, as well as NGOs. So we are making real-time, near real-time impacts on the data sets that are serving a global community. I wanted to tell you that you're probably familiar that once you have these kinds of AI and computing powers, there are a lot more objects that you can start detecting that are relevant for the energy mission. One is very simple. This is work we did almost a decade back, trying to understand, where in the country people were deploying solar panels on different kinds of rooftops. And so it was a big barrier for the community to understand, where are people adopting renewable energy solutions. So these kinds of data sets made a big difference in the energy mission. The other one I wanted to talk about is water, because it's detecting small water was a task given to us from CDC, the Center for Disease Control, when they were interested in understanding if you could detect the small water bodies, which could become the habitats for malaria or mosquitoes, which promotes malaria after big storms. So we took a modified NDWI to extract swimming pool water features, and then looked at the Worldview 2 and 3 imagery, and also the National Agricultural Imagery Program, which is about a 1 meter resolution imagery. And at that time, Titan was the largest machine in the world, and we scaled that algorithm to about 4,000 nodes. And the entire state of Texas, we could process it in about 10 minutes with about 20 megabytes of output, that not only detected every small water feature, and Texas has a lot of swimming pools, but we were also able to get some relative sense about how clean or dirty that water was in those pools, which is an indication of how static that water might have been sitting, which leads to a mosquito habitat. Another powerful applications of AI or GeoAI is detecting mass graves. This is a very current, relevant, and painful topic for all of us as the Ukraine conflict is going on. In the past, the challenge was that, other than humans looking at images, there was no quick way of understanding where these graves are and how many of them there might be. So one of our teams worked on this particular problem of seeing whether you could train a model to detect mass graves very efficiently. And the numbers that you are seeing here is a benchmark of manual interpretation versus the predictions from the AI model, which are remarkably well performing. So here is a very good example, and there's a very narrow, small window of opportunity that exists in this area, because once vegetation starts growing, the graves get mass. So you have to scan a large area very, very rapidly to kind of take into account, detect these graves. So here is an example of where the graves were, and here is the output that came out of the AI model. I wanted to talk quickly about another effort that uses AI and HPC. This is generating high-resolution elevation data at a global scale. And what we are doing, the community has long been dependent on SRTM as a global source. And then you could do active sensing like LiDAR for the nation, but every agency that collects space imagery, we sit on this massive archive of imagery that rarely gets looked at. So we tried to take advantage of this fortuitous pair that were sitting in an archive, and about 40%, 40 degrees angle overlap between particular image pairs. And we wrote a smart algorithm that found these optimal image pairs in a very large archive, and then ported that algorithm to a very large cluster to generate 1 to 2 meter resolution elevation data very, very rapidly. So if I toggle back and forth, you can see the level of details that you can generate out of high resolution. These are 30 to 50 centimeters worldview images that we are processing for the entire planet. And right now, in this benchmark, we are able to create a global coverage in about less than 9 months with a large cluster that we have dedicated towards creating these kind of high resolution data. So these data sets will eventually become cornerstones for understanding flooding, understanding disasters, understanding, our better understanding of our built and unbuilt landscapes. The other thing is, I've been talking about this big HPC, big iron, like how, if you have a very large machine, what can you do? The opportunity is also to see how you can create an ecosystem that goes from a very large machine, very large HPC, to all the way to a very small processor that resides at the edge, okay? So we have been working with the Department of Energy on this project that is trying to test out that actual principle. So as you know, in the US Gulf Coast, we have, every year we have multiple hurricanes that swipe up large areas. And the first thing that goes down is your electricity and communications networks. The challenge is that, although we have many satellites orbiting in space, for the next few days, it's pretty much beautiful pictures of clouds that come from the satellites. And our goal is to see how soon and how quickly can we get the restoration of the infrastructure started. So what we did is we have created an algorithm that is very efficient in detecting an utility pole, like telecommunications or electricity, and it can also look at whether it is upright on the ground or it is collapsed or had a significant tilt after the event. So that algorithm is put on that payload of a drone or multiple drones, which goes out, collects data, and instead of sending imagery, which takes a lot of bandwidth, it finds the best available communications channel. And in most cases, in these kinds of disaster scenario, it turns out to be the satellite communications channel. And since it has that AI smartness, it knows which pole it's looking at, and it sends a small package of data saying the pole is standing versus the pole is damaged. And that data set's coming back in real time to the responders makes a huge difference in terms of how they can properly respond and restore infrastructure. So we are absolutely thrilled about the success of this project, where the algorithms were trained on large machines and now they're being deployed at the edge. One thing that we have ventured out in that might be of interest is to understand how do you create these kinds of a large ecosystem, including de-risking the CubeSats community, because we clearly have a vast and active interest. So we have created a small satellite ground station at Oak Ridge that sits right on top of where I'm sitting. And the goal here is to help the small satellites companies, which are mostly very, very small businesses, understand and overcome research and technology challenges that will allow them to accelerate their technologies. That includes, sensor designs, sensor security, data telemetering, all of the above. So this work has just started. We have 3 partners at present, 2 in SAR and 1 in hyperspectral. And our goal as a national lab is to do the R&D that these individual companies will not be able to afford, because none of them have very large computers or hundreds of people who have expertise in geospatial science, remote sensing, photogrammetry, computing, sensor design. So these multidisciplinary teams, what kind of problems can we solve for this entire industry that will allow them to leapfrog their technology in the future? So I made it sound like I have done everything while you were listening to this talk, but I am forever grateful to have the opportunity at Oak Ridge to work with a fantastic group of people. In my division, we are about 100 scientists and researchers working on anywhere from, with backgrounds in geography, geology, computer science, computational science, electrical engineering, anthropology. And we are all working together to make these wonderful technologies come and serve not just the United States, but a broad global community. So it is an exciting time. It is an exciting time for me personally to have been associated with this field, and to be associated with not just the family that I live with every day at work, but also the broader community and family of geospatial science and the GeoAI and HPC community that I get to be a part of every year at a variety of meetings, including this one. So with that, I'm going to end there, and hopefully there are some questions, and I'm happy to answer them or discuss anything that you may want to from this point onward. So thank you again. Thanks for your attention.
First of all, thank you, because it is really impressive what you are doing in many different fields. As a matter of fact, I believe that all of them, every example you mentioned, deserves a presentation, because there are so many questions and curiosity that came to my mind, but so first of all, congratulations. It's a very, very relevant what you are doing. So congratulations.
Thank
But
you.
then I have some curiosity because you mentioned many projects, like for instance, you were speaking about the digital surface model, the 3D digital surface model. I want to understand, is it available? Are you computing this model only for US or is available everywhere? And in case, how it is possible to get it?
So that's a great question. The images that we are using are commercial, the Maxar worldview images. Right now, this is a project that is funded by particular agencies in the US government. We do not have a global coverage just yet. We are getting there, slowly and steadily. There are lots of end user license agreements and then data quality controls that we have to do. But our expectation is that this is going to become mainstream and publicly accessible data at some point. Now, I should say that we are the science and technology catalyst for these kinds of innovations. We don't own the data. The government owns the data. The government agency that is producing data, they end up owning the data. And at some point, they make the decision on what to take it to the public and what needs to remain for the government use. But we are hopeful that the elevation data will eventually get out to the community.
Yeah, and in this case, I missed which is the resolution of this elevation data? The resolution of the model?
It is between 1 and 2 meters or finer.
It's incredible, simply incredible. Okay, fantastic. And then again, because I suppose that our audience is really interested in the data that are available. You were mentioning typologies of buildings, and you show us also some maps about them. Is they available only for US or it's where is available? And again,
so
because you were speaking about population, you said that is available. The land scan is available for everyone. Yeah,
correct. So the land scan global, that is at kilometer resolution. The land scan USA, which is for the US, and that's the daytime and nighttime. And land scan HD, which is again global, not yet global, but for other countries, but at 90-meter resolution or 3 arcsecond resolution. All those data sets are exposed to the public.
Okay. So I have to check if there is available something for Italy.
Yes, global is, of course, it covers. I don't know exactly from the top of my head if we have done Italy for Landscan HD. The buildings data set that has been QA/QC'd, it is for the US is public. You can find it, on FEMA's, from an outlet of FEMA. For the rest of the world, they are not map quality building outlines. So what we produced out of our HPC is representation of buildings, but they are not made to look like the edges and the corners, sort of the post-processing that you have to do to make it cartographically representative. That aspect doesn't happen unless there is a particular reason for it. We are moving in that directions, but these are, I call them a representation of building on a landscape than the very well-refined boundaries and edges of the buildings like that we have produced for the US.
Okay, so I see that there is one question. So about worldwide digital elevation models, what is the currently available digital surface model but there aren't digital model per ground without the ground cover. Would you expect those to become available soon? So the point is digital surface model versus digital elevation model, removing everything, because sometimes it's very useful. And for sure, I believe that machine learning artificial intelligence can be used.
That's a great question. I should say that the native data that is coming out and the output that is coming out of algorithm is a terrain model. So it's not bare earth. It's just the terrain, the surface. And then we could derive the bare earth, which is also useful. We have not done that quite yet.
Yeah. Okay. Next step. It could be next step. What do you think, Buddha?
Sure. Yes.
Yeah.
Absolutely.
Yeah. So I have another question to you, which is related to the already open available data. You know that I'm also involved in all these open source initiatives, like, for instance, OpenStreetMap. And you were speaking about buildings. So my question is, are you using also OpenStreetMap data for training, testing the machines, or is something that you don't use?
So what we have found, so we routinely look at OpenStreetMap data. Okay? What we have found is that the GeoAI models are extremely fragile and inflexible, and they're very sensitive to the input data. So if your training data is not quite related to the data that you're going to process, the imagery you're going to process, the outputs, the outcomes are not as good as otherwise. So in a lot of cases, we have to derive the training data from the imagery that we are going to process. But we use OpenStreetMap as a reference point to make sure that there's a cross-check, that there are actual buildings out there. And sometimes, we find buildings in places where OpenStreetMap doesn't have buildings. And we have to ensure that, those are true too as well.
Yeah, and that can be useful also for the community, for the OpenStreetMap community, because it means that giving some suggestions about what is needed.
Yeah.
And where is needed to map. So that's very good if it is possible to have, it is possible, as a matter of fact, of having this feedback. And yeah, I want, speaking again about that and the buildings, I imagine that if you want to train the model, there is not just one model, but it really depends on the location, because buildings are very various. And so it means that you are subdividing in homogeneous areas and then training in considering these homogeneous areas, or what is the strategy you are using?
So that's a great. So Dalton Lunga, who's leads our GeoAI team, we recognize this challenge very early on, that it's that models are, the trick is to create generalizable models, and then could you scale these to other geographies? So we were probably one of the first organizations that were trying to do country scale processing. We attempted Nigeria, was one of the first ones, and what we found is that the biggest variable in there was image quality, more than your model. So everything, even though you had uniform training data sets, image quality broke everything. So we have in our workflow pipeline, there is a lot of pre-processing that tries to bring some kind of a quality balance across it. But geographically, was something that Dalton has been, and Dalton and his team has been working very useful. They have a mechanism or approach they're calling ResFlow, which is essentially trying to create, in the lack of a better term, different kinds of categories or baskets that are derived from the pixel characteristics, irrespective of the geography. So when you go into a new, as that library grows, when you go into a new area, you smartly try to match, saying, have I seen these kinds of pixel characteristics before? And if I have, then there is a very strong likelihood that the model I had generated for that particular area would work well here. And that approach is actually allowing us to do good generalization and scaling.
Yeah. Thank you. Thank you for this explanation. And yeah, we have a request by Chain Shine. I don't know if the pronunciation is correct. Sorry. Asking if you can list the websites, access points. Yeah, you already answered. So you mean those data are available at this website. So people who are interested in deepening into the data sets available can go there. Okay, fantastic. I have a very last question to you. Sorry, Buddha, for continuously asking. So my very last question is related to machine learning in general. Because what happened in the last years was that people tended to improve more models. So was more model driven, we can say, machine learning. While now we are realizing that data, and in our case, geospatial data, are so important. And people are starting speaking about data-driven machine learning. And for us, it means geodata-driven machine learning. Do you think that this is reasonable, or do you think that if we can go ahead without data, because there are also some attempts like self-supervised machine learning or semi-supervised machine learning and so on, try to use as less as possible data. Do you think that is possible going toward this direction, or we have to pay attention to the data?
So that's a great question, and I appreciate that question. I have a few different thoughts on it. I think at the end of the day, we are doing data AI more than anything else, right? So it's very data centric. That in the geo world, I agree. I've not seen a lot of process-centric AI. I will also say that our AI approaches are very pixel-centric. And so we have worked a lot with imagery and rasters, then we have tried to apply AI to vector data sets, right? I think it's attractive because we have very, very large archives of satellite images across the world, and various agencies in US, ESA. So it's a very soft, very attractive target. And again, we have not mapped the planet at this resolution ever before. So I see this going on, continuing for some time, and there are very challenging, adventurous, and applaudable efforts that are coming out. People are trying to map every tree in the world, which is, it's a pretty significant effort. But if you think about climate, if you think about sustainability, it is a fundamental data sets that we could create, by mapping every tree. So I don't think that aspect is going to slow down in the near term. What I think is important to understand is, how secure are these AI models? And then there is the other aspects of it is the examples of AI models that we have seen succeed usually have a very large training data sets, right? Or instances of them in the world. So trees, buildings, we have many of these things. I don't know if you start looking for objects that don't exist that many in the world, how successful the AI techniques are going to be in continuous scanning. So the other aspect is, there is a process, an AI-driven process that is required as we are moving towards this CubeSat revolution. So if you believe in what the CubeSat community is essentially promising, and there is no reason not to believe. So I'll take Planet as an example. So Planet was one of the first ones that created this, splash with their doves. And their promise was very simple but very elegant, which is, at 5-meter resolution, map the planet every day. Okay, so at 5-meter resolution, the planet is covered by 100 trillion pixels. So if you want to monitor the planet, which most sustainable development applications, we try to monitor. We want to know what changes are happening, good or bad, right? Agriculture, you want to understand change in agriculture for productivity. And in disasters, you are looking at destruction. So it's good or bad, but you're looking for monitoring change, right? It's not just, do I know where the objects are? How are they changing on the landscape? So how are we going to process 100 trillion pixels every day, 24 hours from data to decisions, right? Even let me say that in agriculture, the rule of thumb is that every 4-day picked image or change is good, because crops don't grow that much in a 24-hour period, 4 days. If you take 4 days, what are you going to do with 100 trillion pixels in 4 days, right? So those kinds of human decision makings will need AI infusion to make that process smart, so we can track these objects and processes of interest on the planet more efficiently. And I'll mention one last thing that I've been thinking quite a bit, although I do not know much about it. When you go to the store and you buy anything, right? They use the optical scanner, and they have the UPC. Every product has that UPC barcode. Okay, so this is machine readable language. So we figured out at one point of time that you don't need OCR, you don't need anything. You can create this UPC barcode that is very fast and very accurate reading by a machine. So at what point of time are we going to say that let's design a satellite sensor that looks at the world like the UPC barcode, right?
Yeah.
Not like the images and the pictures that we are constantly, humans are used to seeing.
Yeah. Yeah.
Right. So that AI is going to be very, very intriguing and cool, but it will be more efficient and more quicker, more accurate. So I'm excited about that possibility.
Yeah, definitely, definitely. It's a challenge, but yeah, we are going toward that, and it's an excellent idea. Yeah, thank you. Okay, but I believe that we have to close here, unfortunately, and I will call back again, Andrea. First of all, thank you so much, Budu. I hope to see you soon somewhere in the world.
Yes.
And thank you, and I leave the word to Andrea.
I thank you very much, Maria and Budu, for this session. And I thanks also the audience for the very engaged participation. We have learned about the GeoAI etymology, because we hear often this word, and we learned that the Budu had a role to play in this definition. It was really an excellent session. I think it was really impressive to learn about the computing capacities, the HPC of Oak Ridge, and all the important work you are doing with geospatial analysis and the data sets that you make are really impressive. And it was impressive also to learn that with your 3,206 GPUs on Summit, you can extract all buildings in a country in a matter of minutes. What was really impressive. I was also very much interested in the discussion on the digital elevation model, because in ITU, we use the publicly available worldwide digital surface model SRTM and ASTER for making propagation predictions for radio communication services, but to improve the accuracy of these ITU propagation models, it would be extremely helpful to have also worldwide digital terrain data sets. So bare ground and in addition, separate ground cover data sets. So it would be, I too would be extremely interested in discussing with you how we could procure this information. And before ending this session, I would like to remind you that on July the 5th, we will host in the ITU several machine learning workshops the day before the AI for Good Global Summit begins, including one on GeoAI, which would be organized by Maria, on building a foundation for geospatial AI, defining a syllabus and body of knowledge. I was wondering if, Maria, you can say a few words on this event.
Yeah, very few words. What is, in my opinion, one of the main problem is that as educators, so professors at the university, we don't have a syllabus, a common syllabus that we can consider for our teachings. And it doesn't exist a body of knowledge about geospatial AI. For sure, we can rely to our colleagues with respect to, in general, machine learning and artificial intelligence. But what I'm asking myself, and also other colleagues are starting asking themselves, is there something special in geospatial AI? And what we need to teach to the young generation in such a way to prepare them for geospatial AI? And that is the point that we want to gather both educators and people from the agencies, people from the private sector, to better understand what are the exigencies on one side, what people are already teaching in their courses, in order to build something that is common. Because again, I believe that every of us is teaching something related to geospatial AI, but I don't see I want to see something more common that we can teach about that. I don't know, Budu, if you agree with me that we needed to find a common view of teaching what is needed and so on, or you think that there is enough?
I would agree. I think it's an important topic to discuss with the next generation.
Okay, and so the point is on the 5th of July to start discussing with some people in Geneva. And now I discover also that this workshop will be also available for people who are not in presence. So will be an hybrid event. And therefore, please stay tuned, because we will put some more pieces of information about that. And all people who are interested, they can contact me, obviously. Okay, thank you, Andrea. Thank you, Budu.
Thank you very much, everyone, for your participation. And with this, let me give back the floor to Anna. Thank you very much. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
you.